This is a sample problem of friction and kinematics. Now, this is the problem. A physics student pulls a 100-kilogram chunk of stone with constant velocity of zero point 0.5 meters per second on a horizontal surface with a horizontal force of 200 newtons. Now, we're going to assume the gravity would be equal to 9.8 meters per second squared. And take note, we encounter constant velocity. The summation of forces is equal to mass times acceleration, but since we are dealing with constant velocity, summation of forces now would be equal to zero. If the rope breaks, how long does it take for the stone to come to rest? This is for letter B. And for letter A, again, we're going to solve for the coefficient of kinetic friction. And for letter C, how far will the stone travel after the rope breaks? Now, let's provide the FBD. We have a person or a student which pushes a huge chunk of stone weighing 100 kilograms. Now, as he pull the stone, this is actually tension, or since in this diagram we're going to represent F for the tension of the cable, where the student uses the cable to push the chunk of stone. And as well, we're going to consider the weight of the chunk of stone as mass times gravity and the normal force, which is the opposing force for the weight. And we have the frictional force here, which is the opposite of the efforts or force exerted by the student. Now, the direction of velocity is also in this motion towards our right. Now, let's start solving this problem. For letter A, we need to sum the forces with respect to the horizontal would be equal to zero. Again, it is equal to zero because we are dealing with constant velocity of zero point 0.5 meters per second. All right, substituting the following values. Okay, since force minus frictional force is equal to zero, okay, motion to the right is positive, so force is positive here, and frictional force is negative because it's towards the left. And then equate it to zero because we are dealing with constant velocity. And afterwards, transpose to the other side of equation frictional force, which gives us with the following relationship as force now would be equal to frictional force. And then remember that friction, and we are dealing with constant velocity, we're going to use mu k or coefficient of kinetic friction. So the force now is equal to our frictional force. This is also equal to the coefficient of kinetic force times the normal force n. And then let's consider the summation of forces with respect to the y-axis. Okay. So we have the following as n, positive n, since upward minus the weight mass times gravity would be equal to zero since this is constant velocity. Now transpose to the other side of equation weight, this becomes normal force is equal to mass times gravity. And since force now is equal to coefficient of kinetic friction times the normal force, if we're going to substitute the formula for the normal force, which is mass times gravity, this becomes kinetic of coefficient or coefficients of kinetic friction times mass times gravity. Now, this is the value for the force. Thus, if we're solving for the coefficients of kinetic friction for letter A, manipulate this formula, divide both sides of equation with mass times gravity. This gives us with mu k is equal to force all over mass times gravity. All right, let's substitute or plug in the given values. We have our horizontal force at 200 newtons all over the mass of the stone as 100 kilograms times our gravitational constant here on planet Earth at 9.8 meters per second squared. Further simplifying, This quantitative values gives us mu k now at zero point 0.2. Now, for letter B, if the rope breaks, how long does it take for the stone to come at rest? We're going to consider the following analysis as summation of f of x would be equal to negative frictional force equal to the mass times acceleration. And remember that our friction force here is equal to kinetic of coefficient of friction times our normal force. And since this is negative, we're going to make this negative as well. So mass times acceleration is equal to negative kinetic friction coefficient times the normal force. And solving for the acceleration, this gives us the following new conformation of the equation as acceleration is equal to negative kinetic friction coefficient times normal force all over the mass of the block. But normal force is equal to mass times gravity. And if we're going to substitute this one into our previous equation, our acceleration now becomes the kinetic of friction coefficient times mass times gravity all over our mass, and the mass cancels out. And for solving the velocity, we're going to use this following equation as the final velocity v is equal to initial velocity vo plus at. But since once the rope breaks, our final velocity will come to rest. So our final velocity would now be equal to 0. So 0 is equal to initial velocity plus acceleration times time. Hence, if we're going to solve now our acceleration from this equation, since mass and mass cancels out, we are left with kinetic friction coefficient times gravity, and substituting our values, this gives us our mu k from our solved value in letter A at 0 0.2. So 0 0.2 times 9.8 meters per second squared. This gives us negative 1.96 or negative 1.96 meters per second squared. Now, this is our acceleration. Now, how are we going to determine time? If we're going to manipulate this equation, 0 is equal to initial velocity VO plus acceleration times time. Okay. And then if we're going to transpose initial velocity to the other side of the equation, this becomes negative VO all over A. And substituting the following given values, we have our velocity 0.5 meters per second. So this is negative 0.5 meters per second all over our acceleration at negative 1.96 meters per second squared. This gives us a value of answer for letter B, wherein it takes 0.26 seconds for the rope to break. So the rope is actually weak. Now for letter C, how far will the stone travel after the rope breaks? Now we're going to use this formula in kinematics as distance is equal to initial velocity times time plus half of acceleration times squared all over, or half of acceleration times time squared, or acceleration times time squared all over 2. All right, substituting the following values gives us the initial velocity, 0.5 meters per second, times the time in letter B at 0.26 seconds. This is our solved time in letter B, plus half of the solved acceleration in letter B, negative 1.96 meters per second squared, times our time from our solved value in letter B at 0.26. So this is squared. This gives us our final value for the distance, okay, after the rope breaks is at 6 centimeters. So it's really short, okay? At 16 centimeters, the rope breaks. So the student used a rope that is weak.